All right, welcome everybody. Welcome on in. It looks like we have some assignments that are due relatively soon, right here in the near future, September 27th. So that's some work to do with functions. So I feel like I probably should go over that so that you have some time to get that stuff done before it's due. So we've talked a little bit about functions before, but math, especially algebra right now, is really taught from a perspective of functions. It doesn't have to be. Sometimes people get the idea that functions are the most important thing that there is. Functions are really important, but many of you will run across times when functions are not necessarily, you're dealing with something that's not a function, right? You do this when you do conic sections. So those of you who are taking Math 3 intermediate algebra, you'll deal with conic sections. Those are not functions. And there's other times when functions come up, things that aren't functions come up. But it's really convenient to know how to deal with a function when you are dealing with a function, right? So we'll look at this functions 0-1 part, and then later we'll move on to the systems of equations and stuff that we have to look at. Yeah, that's a good timeline. So where was I? Right here. So let me give you a little bit of an introduction into functions and the different, we'll look at the different types of homework problems so you can see how we're supposed to deal with functions. So what is a function? A function is basically, it's just a type of relation, which doesn't help because you go, well, what's a relation? A relation is where you have an input and an output, and each input goes to one output. So I could have a function that says 1 goes to 5 and 4 goes to 7, right? And you might wonder, well, why would I need something like that? Well, functions get used all the time, say like at the grocery store, when that little thing scans the UPC code, it basically looks up that code and says, give me a price, right? So it goes in there. The input is the UPC code. Is that the UPC code? Whatever they're called, the barcode that's on the, maybe UPC something different. But there's the barcode, that's on the thing. You scan it. Basically, that's the input. It goes into the computer, and what the computer returns is a price and says, this is how much that thing costs, right? That's an example of a function. There's a function that exists inside of that computer that changes barcodes into prices. So the input is a barcode. The output is a price. Now, function like that's an example of a relation. That's also an example of a function, but functions are very special relations in that a function has this restriction that if you put something in, only one thing should come out, right? And you can imagine why that would be a problem. What if you were at the grocery store and you scanned your item that you wanted to buy, and the computer came back and said, that item costs $3.99. It also costs $4.99. You'd be confused. You'd go, wait, how can this item have two different prices? That doesn't make any sense to me. What am I supposed to pay? Is it $3.99 or is it $4.99? That would be confusing, right? So with a function, we have this added restriction that for one input, you only get one output. So for a function, the barcode should not return two prices. It shouldn't return $3.99 and $4.99. That causes problems. It can only return $3.99 or $4.99 or whatever the price happens to be. That's essentially what a function says, is you put in one input, you get one output. That's not always the case. So for instance, we can think of that on the graph. The inputs are our x's and the outputs are our y's. So something like this, y equals x squared. This is an example of a function. If you notice, for any x value you pick, there's only one y value, right? So what about when x equals 2? Well, I followed up and goes, oh, my y equals 4. Just one answer, right? When x equals 0, my y equals 0. Just one answer, right? So that's a function. So what if we had something like this? Something like that. Not a function now, right? Because I go, well, okay, what about at 2? What is my function value at 2? Well, it's this y value up here, but it's also this y value down here. Oh, that's confusing. Now we're back in that situation of getting two answers, or 2 outputs for 1 question, 1 input, right? That's what we don't want. So a circle is not a function because, like, what about at 0? What is my output at 0? Well, it's 5. It's also -5. No, can't be a function then. If I ask a question, I only want 1 answer, right? So if we ask this relation a question, it gives us 2 answers. When I ask, when x is 0, what is y? Oh, it's 5 and it's -5. That's no good. So at least for now, you'll deal with these in intermediate algebra. So you'll deal with circles in intermediate algebra. But for the remainder of this class, we largely deal with things that are only functions, which is convenient, right? So you don't have to worry about things like this. What you do want to know is how to tell if something's a function or not. And we have a nice, easy, clean way of doing that graphically. If you think about it, we can take a vertical line. Here, see my vertical line that's scanning over my picture here? If you take your vertical line and it ever touches your graph 2 times at once, then that thing's not a function, right? Because if you think about it, well, what does it mean if the graph is touching the line 2 times at once? That means there's 2 y values for a single x value, right? This line has a single x value, 0, and yet it's touching our graph at y equals 5 and y equals -5. Well, then therefore, this must not obey functions at this point. What about over here? Oh yeah, at this x value, I'm getting this y value. I'm also getting this y value down here. So can't be a function. All right, what about this? Here, what if I scan my vertical line over this? Notice how it ever only hits the graph once at a time? It's hitting it at different points, but never at the same time. So this is a function. This is what we call the vertical line test. And you can just do this visually in your head. Just take the graph you're looking at and scan a vertical line over it. And if it ever hits it twice at the same time, not a function. If it always only hits it once, then it is a function. Sometimes people will go, like sometimes people do this, and they go, but this is a function because, look, I can put the line right here, and it only hits it once. Well, that doesn't change the fact that it fails to be a function in all these other places. So it's not that you're trying to find a place that passes the vertical line test. You're trying to find a single point of failure. If it fails the vertical line test in one spot, it fails the vertical line test. Okay, so that's where we're at with that. You just pass a vertical line over it. If it touches the graph 2 places at once, the thing is not a function. So a very quick, easy way to tell, if something's a function or not. Okay? We don't have to worry about those circles anymore for now. So that's our quick version of a function. Now, one of the things that's confusing about functions is I think most people kind of get functions, and they even get a couple ways of dealing with them. The problem is we're going to have like 4 different ways of interacting with functions. And you really kind of have to be comfortable with all of them. One way that we dealt with a function is what we just looked at, graphically. We looked at the graph of a function. We're also going to have function notation, right? And then we're going to do later in this course and your next course, those of you who are going to take intermediate algebra, you do some different ways of dealing with functions in those classes as well. But the main 2 ways that we're going to deal with functions is graphically, like we just looked, and algebraically, where we use what's called function notation, right? You'll get in the homework, sometimes you'll get where they do diagrams of a function, and you have to kind of look at it, and you go, okay, I see what the inputs are, I see what the outputs are. But most of the time, we're going to deal with regular function notation and then graphs. So, for instance, let's go back to this one. How would I deal with this as a function? Well, you could say, what is my y value when x equals 2? Right? This is what we do a lot of time with functions is we ask, we give an x value and we ask, what's the y value? So when x is 2, what's the y value? Well, I go over to x equals 2, and what's my point on the graph that corresponds to x equals 2? It looks like it's this one. It looks like it's 2, 4. So let's graph that. 2, 4, and look, the y value or the x value of 2 corresponds to a y value of 4. Therefore, 2, 4 is a point on this graph. So when x is 2, y is 4. That's the kind of way we look at it from the graph. People struggle with this one. The algebra people usually get, so for instance, let's do it algebraically now. So the way we would do this is we give the function a name, and generally we name the function a letter. It's just easy to do. Oftentimes we call it f for function. But if you happen to be dealing with a particular function that means something, you might want to use that letter, right? Because it gets less confusing, especially when there's going to be problems in your future where you'll have more than one function per problem. And a lot of times, if we have two functions, we'll call them f and g. F for function, and then you just go to the next letter of the alphabet, g. But sometimes, what if you're in a class or you're doing a problem that has to do with business? Well, you might want to call your cost function C, and you might want to call your revenue function R, and your profit function P, and then you're not going to mix them up on accident, right? If you just give them arbitrary names, it's easy to mix them up. But if you call them R, C, and P, you're probably going to know which one's revenue, cost, and profit. You're not going to mix them up. So feel free to do that, okay? But here, what I'm about to show you is the algebraic version of what we just did graphically. So we would call this f of x equals x squared. That was the function that I put in graphically, y equals x squared over here, right? We could also write this as f of x. See, it's giving me the same graph. Why is that? F of x and y mean the same thing. F of x means put x into the function f, and y means what's the y value that's associated to the x. It's two different ways of saying the same thing. And you'll actually do this in intermediate algebra. When you solve for inverses, you'll change this f of x into a y. You'll do a bunch of work, and then you'll change it back to function notation. Right? They're interchangeable, okay? Which, again, is another one of those little confusing pieces. Okay, what does this mean? Well, let's say I wanted to, what did we just do? We figured out f of 5, so f of 5. So this means that what we're going to do is we're going to replace, oops, we got a unmuted person. Did you have a question or? Oh, there we go. If you have a question, that's fine. We're going to replace the x with the letter or with the number that we're inputting into the function. Now, right now, we're inputting numbers. You don't have to input numbers. You can input names. Right? I gave the example a little while ago of a barcode. You can input all sorts of things into functions. But for now, we're keeping it simple with numbers. So this says you take the input and you square it. Oh, it wasn't 5 that I did either. It was 2, wasn't it? So this would be 2 squared, which would equal 4. So see how we're getting the same numbers? It's just one time we did it from a graph and one time we did it from the function notation. Now, usually the functional notation is the most convenient way to deal with functions, but sometimes it's not an option. Sometimes you're going to do a problem where they give you a graph and they say, here's the function, and there is no function notation for it. There is no nice, clean way of writing it. You have to get your x's and y's from looking at the points that are in the graph. Okay, so that's why you want to be able to go back and forth. A lot of times students go, I'm comfortable with function notation. I'm just always going to do it that way. Well, that's fine until all of a sudden you do a problem where the function notation is not available and you don't get it. You have to be able to look at that graph and figure out what your x's are and what your y's are. Okay, so let's look at a couple problems here. Evaluate functions. Remember, evaluate is just a fancy word that means substitute this into your problem. So here we have h of x equals 4x minus 4, and we want to find h of negative 3. Okay, so let's look at that. H of x equals 4x minus 4. H of x is equal to 4x minus 4. And they want us to find what? They want us to find h of negative 3. Okay, h of negative 3. Okay, so let's let this pop up. Okay, so here's basically our problem. h of x equals 4x minus 4, and we're asked to find h of negative 3. Now, what they're saying here is take your expression, 4x minus 4, and everywhere there's an x, you're going to substitute in a negative 3. So this would become 4, negative 3, minus 4. See how it looks just like the line above it as soon as it compiles here? It looks just like the line above it, except the x has been changed to the negative 3, which is our x value. It's the input, right? This x has become a negative 3, so this x has become a negative 3. And then from there, we just sort of simplify, right? So that would be what? Negative 12 minus 4. Negative 12 minus 4 should be negative 16. Let's see. There we go. Got it right. See? They're the same thing. It looks exactly like what I did. All they're doing is substituting the negative 3 in there for the x, and then, of course, using order of operations and all that kind of stuff that you're supposed to do. But that's really all there is to that type of problem. All right, let's do a level 2 problem. Let's see what that looks like. See, these are just a little bit more complicated. This is a good one because you have to be careful with your negatives. I see people starting to do weird stuff with their negatives. So let's go through this one because order of operations is important. A lot of people go, yeah, I know my order of operations. I'm following it. But then when we trace back what they're doing wrong, it is that they're doing order of operations wrong. So let's try this one. F of x is negative x squared plus 10. So f of x is negative x squared. Was it minus 10 or plus 10? Minus 10. And we want f of negative 4. Okay. Oops. Okay, so how are we going to do this one? Well, first we need to understand what we're looking at. That negative x squared is the part that confuses people. It's that negative in front of the x squared that throws people off. You want to remember the difference between these two things. There is negative x squared, because people, this is like a very common thing to forget in mathematics. And then there is negative x squared. Okay, see those two ways of writing that? Those mean very different things. You might look at it and go, it doesn't seem like the parentheses really making much difference. It is. Remember your order of operations, right? What do we have going on here? We have a multiplication by a negative 1, and we have an exponent. So according to order of operations, are we supposed to do multiplications first, or are we supposed to do exponents first? We are supposed to do exponents first, right? So a lot of times people will want to do this negative first. No, our order of operations says you do the squaring first, and then you multiply by negative 1. That's different than this case, which says take negative x and square it, right? This is saying the square applies to everything in the parentheses. So that's different because, remember, parentheses take precedence over exponents. So this one's specifically telling us to do it first. So this version right here with the parentheses, that's actually how people interpret this a lot of times, and then that leads to confusion for them, right? So what you want to remember is order of operations, do the squaring, then multiply by a negative, and then subtract 10. Okay, so let's go back up. Let's go back up here. So if I'm, actually, let me do it on that same line. Okay, so that means I'm going to have negative. Now I'm substituting in a negative 4 squared minus 10. Oops, the square should be, sorry, my parentheses should be over here. There we go. That's what that should look like. So this negative out in front, that's this negative right here. Those are the same negative. And then the x just became a negative 4 in parentheses. Now, I put it in parentheses so that we could keep track of this negative, and remember that's actually part of our substitution because it's -4 that we're putting in for x. So I have -4 squared minus 10. Well, if I square -4, I get 16. And then with this minus in front, it becomes -16 minus 10 is -26. Let me write that out in a couple steps just so I'm not losing anybody along the way. So this would equal -16 minus 10. Does everyone see why it's -16? When you square -4, you get a positive 16, but then you have that additional negative out in front, making it -16. So the whole thing should equal -26, assuming I wrote everything down right. -26. And there we go. Okay. See, and they write it the same way with the parentheses. Okay, so that's how that problem works. Okay, so not too bad. All you're doing is whatever the number that they give you to plug in, you just replace x with that number, follow your order of operations. Now is where we start getting into the stuff where people find it a little bit tricky. This is where I have students come to me and go, I am confused. I know how to do function notation, but we usually do that algebraically. What am I supposed to do on the graph? Well, remember that a point on the function is just something that fits the function rule, right? So the x and y pair on a graph are indications that they fit this function. So f of -4, what am I going to do? That's my x value, right? So I'm going to go to, let me blow this up. It's a little small. There, that looks a little bit better. I think you can see a little bit better now. So I'm looking at f of -4. So remember, that's my x. The x is the thing we're putting into the function. And see, they even remind you the x is inside the parentheses. The y is the thing that comes out. It's the thing we're getting back, right? The x is horizontal. The y is vertical. So my x is -4, so I find -4 on my x-axis and go, where's my point? Oh, it looks like it's right here. A little inexact, but it looks like it's right there at -2. So when -4 is an input into the graph, -2 is an output. Right? And look at that. We didn't even have to calculate anything. Even in those last problems we did, which were fairly straightforward problems, we still had to do calculations, right? Here you don't. You just look at the graph and go, well, when x is -4, looks like my y value is -2, right? So we'll go -2, and there we go. We got it. See how they draw this little line here? That's what you should be doing visually in your head. Okay, when my x is -4, my y is -2. I can see it coming over here. Okay, let's do another one. Okay, here we've got this. We want f of -2. So I go to -2 on the graph. I find the point associated to that, which would be this one right here. Looks like our answer is -2 again. All right, let's do one more. Okay, f of -4. In this case, I have to go up. It looks like my y value for an x of -4, my y value is 5. Right, we got it. Okay, so you might be watching this now, and probably some of you are going, that's super easy. And then some of you are going, I'm completely confused. I don't understand what's going on. That tends to be the reaction. Is some people are like, yeah, that's very simple. And some people just completely don't see the x and y. So if you're still confused about that, don't be afraid to ask questions, right? Ask the question and I can kind of help you out. But this picture does a good job explaining it. When x is -4, you find the point on the graph that has that x value, and then you just figure out what the y value is. The height is 5. So you go from there, okay? So please ask if you have a question on how to do that, but that's basically how that works. Then we graduate into something called a piecewise function. A piecewise function, you can kind of think of it as like a Frankenstein function. It's a bunch of different pieces that are unrelated put together to create one new thing. Okay, so let's take a look at, let's do piecewise functions graphically first because it goes along with what we were just talking about. So this is a piecewise function, just there's different pieces. So almost all of the time your function's a parabola except right at x equals 1 where you get this point up here. So the circle means it's not a point right there. There's like a hole, but it exists right up here. So they say evaluate the function graphically. They want us to find f of -2. Okay, so we just play the same game. Like, the piecewise function doesn't really change very much when you're looking at the graph. You play the same game that we were just playing. I'm going to find -2 on the x-axis because that's what they're asking for, right? F of -2, that's my x. So I go to -2, and it looks like I'm going to go up to 3. My y value is 3 right here. So I'm going to go 3, submit answer. We got it. See? So same thing we did before. You're just looking at x equals -2. That happened right at 3. Okay, let's look at another one because these can take different shapes. So here, this one looks even a little bit different. What is this? This is a parabola and a line together, right? So see how you get kind of a Frankenstein type thing. We've got a line and we attached it to a parabola, and also there's a hole in it. So all sorts of different stuff going on. And they say, what's f of 2? So people get really confused here, and they're like, what am I looking at? There's a parabola and a hole and a line. What's going on? Just do the same thing that we've been doing. Don't overthink it. This is one of those sections that people overthink. Don't overthink it. Go to 2. Okay, x equals 2 is right here. So I'm going to find where the graph is. It looks like my y value is -9. So for an x of 2, my y value is -9. So I go in here. -9, submit answer, yes, and we're good. Let's try another one. Here's another one with a line and a hole in it. F of 6, you go over to 6. It looks like my y value is -6. So I'll stick that in there. Get it right. Let's see what the next one looks like here. So they do a few of these lines with a hole in it. I'm trying to see if we can get to one that's a little more interesting. So f of 5, so you'd go to 5 here. Oh, so this one is interesting. Look, here's one. The point they're asking about is actually where that hole exists. So this is where you have to know what you're looking at. The hollow hole or the empty hole, that means the point is not there. So all the way up to that really, really close, the points are getting really close to this height of 3. But right at x equals 5, we say the value is actually 2. See where the solid dot is? So here at x equals 5, we actually are looking at the filled in dot. That's the one that counts. So we want a y value of 2. And then it goes, yeah, good, you got that, right? Because we looked at it. Notice right here, it's ignoring the hollow dot, and it's paying attention. It's respecting the filled in dot. Right? So that's what you do when it's right at that kind of point. And then here we have another line with a parabola and then a dot, and they want us to know f of 3. Okay, that's right at the weird point. Look at x equals 3. Look, we've got a hollow dot, a solid dot, and another hollow dot. Well, remember, the hollow dots just mean the point is getting close to there, but at x equals 3, all we really care about is this solid dot right now, right? When those of you who are going on to calculus, you'll do fancier stuff with graphs like this, but you don't have to worry about that till then. For now, all you have to be able to do is take the x input of 3, say, oh, well, here's my point, so my y output must be -2. And there you go. We got it. Okay? That's how you deal with piecewise functions graphically. Okay? So hopefully you kind of see it's basically the same game as dealing with non-piecewise functions. You do it the same way when you're doing it from the graph. All right, let's evaluate piecewise functions from algebraically. So let's look at that. So here's one. Now that looks weird, right? That notation looks like it's a mess. What is going on here? Well, if you think about it, it's very, like, if you erase this extra stuff right here, it's going to look just like the function notation we're used to, where it would say like f of x equals 1/2 x plus 7. It's just giving you a rule for your function. It's telling you when you have an input, here's what you're supposed to do with it. Well, this function has two rules. And you might go, well, wait a minute. You told us that a function is supposed to only have one output. So if I have two different rules, then doesn't that mean that I would get two different outputs and then it's not a function? And that's a good way of thinking about it. But the complete story is you don't use both rules. You only ever use one rule at a time. So we have a rule that says sometimes our y value is going to be 1/2 x plus 7. And we have another rule that says sometimes our y value is going to be x minus 3 squared with a negative in front. You go, okay, well, that's good, but how am I supposed to know which one I'm supposed to use when? How do I know when to do that? And the answer is this over here. This over here tells you when to do it based on your x value. For this extra step right here really confuses some people. It's not nearly as complicated as people kind of think it is. So don't think, like, don't keep digging like it's really, really complicated. Just consider that this is an x, right? The one that we're being asked about, ask yourself, is that an x value or a y value? This is an x value, right? Okay. Well, look at our conditions over here. This says use the top rule when x is less than -4. Use the bottom rule when x is greater than 2. So we have to figure out which one it is. Well, is 1 less than -4? No. Is 1 greater than 2? No. So actually our function isn't even defined at x equals 1, so undefined. Submit answer, and we get it. Okay? Let's try another one where it's actually defined. Okay, here we have, wow, this one has 3 rules in it. 3 rules that we have to pay attention to, and we want when x is equal to 5. Okay, so when is x equal to 5? Let's see. Is 5 less than 2? No. Is 5 equal to 2? No. Is 5 greater than 2? Yes. Okay, so that means we're supposed to use the bottom rule here. The bottom rule says to take the negative of your input, which would be -5, and add 3, which should give us -2. And there we go, right? So it's telling us, this right here is telling us we're supposed to use the bottom rule for this particular x equals 5, and then we go over and calculate it over there, okay? They even have a graph. So if you wanted to do this graphically, you could do it that way as well. Okay. Okay, so I'm going to give you a minute or so, roughly. I'm going to give you a moment, I should say. Try to see if you can figure out how you should do this. So just walk yourself through the procedure and ask yourself, should I be using the top rule or should I be using the bottom rule? And then once you decide which rule you're supposed to use, what is your output? What is your y value that should come out from this function? So I'm going to give you a few seconds, I don't know, whatever, 10, 15, 20 seconds to try to answer those questions. Do I use the first rule or the second rule? And if I do that, what is my answer? So go ahead, think about that for a minute. Okay, hopefully you had a minute to think about it. So let's see. Well, the way we know if I use the top rule or the bottom rule is by comparing our x value to these conditions over here. So is -1 less than or equal to -5? No. Is -1 greater than 5? No. Right, it's kind of in between those values. So it's the undefined situation, and we got it. Okay. Let's try that. Let's try another one. What about this one? This is not one we've seen exactly. One is for when x equals 3, and one is for when x is not equal to 3. So let's see. The value they gave us was 3. So is 3 not equal to 3? No, that sounds silly to even say, right? 3 is equal to 3. So we want this case down here. That must mean that our function output is 4. It's telling us that's the value 4. And some people get panicked when there's no x here. They're like, well, I'm trying to plug the 3 into an x, but there's no x there to plug it into. Right, it's just telling you your output is 4. Your y value is 4. Right? Sometimes there's not going to be an x, so people get overwhelmed looking for an x. Sometimes it's not there. Okay, let's see what the next one looks like. Okay, top rule or bottom rule? Just give yourself 5 seconds to think about it. Are we using the top rule or are we using the bottom rule? And if so, what's the output? Okay, so what they're telling us here is that for any x values that are between -1 and 2, use the top rule. For anything that's between 2 and 5, use the bottom rule. Well, 3 is not between -1 and 2. It is between 2 and 5, so I should be using this rule. So it looks like our answer is -4. Okay, see how that works? Not hearing any, I'm not seeing any questions, so feel free to. Oh, sorry, I had my streaming software kind of went weird for a second. So those of you watching on YouTube, it probably went weird for a second. I think we're good now. Okay, let's do graphing piecewise functions because those are confusing. Okay. Graph the following functions on the axis provided. So I'm going to show you what usually, or not usually, but a lot of times what I see. I need to shrink this so it'll fit on the page here. Here's what I sometimes actually. Yeah. So remember on the right side, that's telling you where that graph exists. So we only want it to exist over those areas. So this says we have the graph -x minus 3. So let's think about that for a minute. What would the graph of -x minus 3 look like? Well, that looks like it's in y equals mx plus b form, right? Where m is -1 and b is -3. So we go over to -3. That would be our intercept. So we could do this, and then the slope is what? -1, so it's going to be like this. And then we could actually extend it, oops, like that. But that's not right, because this is just the line -x minus 3. So what's going on? Like, what's happening with this? Well, for one thing, it's only supposed to go from -6 to +4. You can see we go past 4 on the right, and we go past -6 on the left. So we've definitely covered too much ground. But there's another problem point, -1. Our graph, like, do you notice that neither one of these says equal to -1? Our graph shouldn't exist at -1. It should be one of those, we should have that hole on here. So, like that. And actually, it shouldn't even be going up to this part. It should only go to -1. Let's erase this. So if we start at x equals -1, that's going to be what, at -2? And it's going to go up to x equals 6, like that. And these should be hollow dots. How do I know that? Because it's not x is greater than or equal to -6, it's just greater than. So we don't include the endpoint. If it had another little line here for or equal to, you'd have a solid dot. Here we have an empty dot. Now we have a line from -1 to 4. It's the same line. So we're going to go, let's see. This one's going to go here. Hollow dots on the end again. Should look like that. Let's see, did I get everything lined up right? Sometimes it's hard to tell if you got it perfect. Looks like we nailed it. Okay, does that make sense? Basically, you're just graphing these lines, but you only graph it over this area. What I see is people cover the entire graph with all the different graphs, but keep in mind that would fail the vertical line test, meaning it's not a function, right? So let's look at another one. Okay, the line 2x plus 6 when x is less than or equal to -4, and x minus 3 when x is greater than or equal to 1. You might want to plot points for this. Let's do it a different way. Let's look at 2x plus 6 when x is less than or equal to -4. So what would -4 be when I plug it in here? I'd get -8 plus 6 would be -2. So that means we have the point -4, -2. That's a point that I care about right there. And then what? Our slope is 2 over 1. So we're going to be up 2 over 1, up 2 over 1. And we just kind of do that forever. So it's going to be, what, like this? And notice it's a solid dot because of the or equal to piece right there. Okay. So that's the top part. Notice how this line doesn't extend. Why am I not drawing this line to extend way down here? Because it's only for x's that are less than or equal to -4. -3 is not less than or equal to -4. So we don't cover this part of the graph with that line. Okay. Now we take the bottom. Oh, it's x minus 3. So a slope of 1 with an intercept of -3, and that happens at -1. So for x equals -1, we're going to go what? Down here and go something like this. Right? See how this line does not go over to this part of the graph, and this line does not go over to this part of the graph? There's a gap. That's how that's supposed to look. Uh-oh. What did I do wrong? Sometimes you got to look at the graph if you get it in just the right point. Oh. Oh, see, I wasn't careful enough. I thought I was going up one over one, see how it kind of looks like it, but then when you follow it, you can see I got off track. So my slope was 1 over here, but I was a little sloppy with how I was drawing it. So let's go here. Be real careful with my points. Is that it? Nope. There we go. That one's right. So I think I was down 1. It's hard. Like, take your time to make sure they line up right. Let's try that again. Oh, wait a minute. Oh, it was the other one that was the problem. My slope was messed up there. Let's try another one. For some reason, I was thinking negative slope when we did that one. Let's try one here. Okay, here's a good one because this one will throw people. So between -4 and +2, we want to use this line with the slope -1 and a -2 for its intercept. So that means we're looking at, so between -4, this x right here, -4, and this x right here too. So we want a negative slope, and we're at -2, and it's a -1 slope. So just use your information from that chapter where we did slope and intercept. And then to make this follow through to 2, I can just extend it. Except now these have to be hollow on the ends, right? Because they're less than, not less than or equal to. So that should be this part. Now what's this? What about 4? If your y values are always 4, what is that going to be? What does that look like? Well, that looks like a horizontal line at y equals 4, and it goes from 2 to 6. So from x equals 2 over to x equals 6, but we've got those hollow dots, so you click those dots. Just want to make sure I don't want to get this one wrong. When you're doing them on the fly like that, sometimes it's easy to miss something. Okay, so see how that works? Let's try one more, because I know students struggle with these. Let's do another one. Okay. Graph the following on the axes provided. So from -5 to 2, so from x equals -5 up to 2, we want the graph -2x minus 1. So for negative 1, I don't know why I was thinking the positive slope on the last one. It was clearly not right. So we want to go up 2 over 1 like this. Oh, also, let me show you the other way you can do this. Here's a convenient way of doing this. Let's take negative 2x minus 1, negative 2x minus 1 from x equals negative 5 to 2, negative 5 to 2. So if it's a line, like a bunch of these that they're giving us are lines, they're in y equals mx plus b form, but sometimes they're not by the intercept, so it can be a little trickier to see where they go. You can just evaluate those. So when we have x equals negative 5, then we can calculate this. Negative 2 times negative 5 minus 1 equals, that's going to be what? Positive 10 minus 1 is 9. Does that make sense? Negative 2x minus 1 from negative 5 would be positive 10 minus 1 should be 9. So that gives us the point oh, sorry, I was showing the wrong screen there. So from negative 2x minus 1, from x equals negative 5 to 2, just plug in these endpoints. So when x is equal to negative 5, we get 9. So the point we care about will be negative 5, 9. Okay, so what's the other point we need? Now we tried it 2. When x equals 2, then we get negative 2 times 2 minus 1. So that's negative 4 minus 1 equals negative 5. So that gives us the point 2 comma negative 5. Let me make sure that makes sense. If we put a 2 in there, we get negative 4 minus 1 is negative 5. And those should be, okay, so let's see when I go to graph this. So negative 5, 9, and 2, negative 5. So negative 5, 9. And then 2, what was it, negative 5? And then we can just double check. Does this have a slope of negative 2? Yeah, it does. And does it have an intercept of negative 1? Yeah. But careful, we're not quite done. Remember, this doesn't have the or equal parts, so the ends should be open like that. All right, and then you can go from there. Okay, and I'm out of time. So that's how you do all that piecewise stuff. So I know it looks really confusing at first. Once you get the hang of it, you'll just zip right through it. Like once you see how the x's and y's work, you'll just fly through it. Okay, so please see me if you have questions or need help or concerns or anything like that, and I can help you out with that. I'm not seeing any questions today, so I assume people are relatively comfortable with this. And all right, so feel free to hop into Zoom and ask me questions. Otherwise, I will see you next week. Thanks, everybody.